So if momentum is not conserved in this frame of reference, we need to change how we think of mass. Make sense? So this is moving up at 8, this is moving down at 10. This thing's mass is going to have to increase. And exactly how much will it increase by? Well, it'll increase by the same amount that the time increased by, right? If we have a value in kilogram meters per second for momentum, then if the seconds are increasing, then the kilograms must also increase. And that way, we can keep our conservation of momentum. So, here's how we end up changing the mass. This equation should start to be looking pretty familiar by now, especially this factor on the bottom. We can see that if we graph this, it'll look very similar to our time dilation graph, if not identical. So this increase in momentum is called mass dilation, just like the increase in a time interval is called time dilation. So we can see that as a particle or any object gets closer and closer to the speed of light, it becomes heavier and heavier and heavier. Once we get to about 85% of the speed of light, we end up weighing or having a mass twice as large as when we were stationary, right? Now this leads to all sorts of interesting effects. It means that if we accelerate a small particle to very, very high speeds, when it hits its target, it behaves like it has a huge amount of mass. And a lot of energy is released. So fast-moving things have more momentum than you would expect. We already know that if an object moves faster, it'll have more momentum, right? P equals mv, so if we double our speed, we double our momentum. Except that because of mass dilation, in reality, if we double our speed, we will slightly more than double our momentum because the mass will increase as well. And we can observe this in particle accelerators. Let me give you an example. In the Large Hadron Collider, which is the largest particle accelerator in the world, protons can get up to within a few meters per second of the speed of light. And when their mass is measured, it's measured to be about 7,000 times greater than when the protons were stationary. So it's easy to see that mass dilation is a real effect that really does happen. Now, these three effects, that is time dilation, length contraction, and mass dilation, are known as Lorentz transformations. They're named after Hendrik Lorentz, of course. So Lorentz figured out these equations and transformations before Einstein figured out his theory of relativity. He didn't really know what they would be useful for, but obviously, as we can see, they came in handy. So that's the end of the theory. We've learned about mass dilation. We've seen a thought experiment as to how it arises. And we know exactly how much the mass will increase based on how fast the object is moving.